dilute BEC.
Oh, very fancy.
Just going to change this around if you don't
Sure.
mind.
Yeah.
It's just people more speak this.
Got it. Yeah. All right. Can everyone hear me? Yeah? Okay. So hello, I am Maren Mossman. And I just wanted, just like everyone else, to thank the organizers for inviting me here. I'm an assistant professor, so I'm only in my third year. So I'm going to be talking about some work that I've done with Peter Engels, who talked at the beginning of the week. And then at the end, I'll talk about kind of what our future directions are and what kind of theory collaborators I'm looking for in my research group. Okay, so we also would like to acknowledge funding from the NSF, as well as the Henry Luce Foundation, which is how I am funded. Okay, so our theory support for this work is mainly Michael Forbes. Let's see if I can get a laser pointer. Look at that, Michael Forbes, who's at WSU, as well as his research group at WSU. So a lot of the numerics were done by Ted Delicatney, who has now graduated. And some of the more recent work has been supported by Ryan Corbin. All right, so you saw this slide earlier in the week. This was a slide directly from Peter's talk. And over the last week, we've seen a lot of different applications, really cool physical applications for dispersive hydrodynamics, shock waves, and today, what we're going to be talking about is what happens when you take away interactions. Okay, but you still have dispersion. Okay, so we're going to be looking at some beautiful pictures, so I hope you enjoy this pre-lunch talk where you can just sit back and relax. There is not much math in my talk, but there are many, many beautiful pictures. Okay, so I'm going to first start with some motivation and background, so we're going to use a minimal model, if you will say, and we're going to compare what we would expect to see in an interacting system versus what we see in what the system that we've created is. I'm going to be your tour guide on the road to catastrophe, and then we're going to look at a different type of potential and then some future directions that we are going to be going. All right, so the motivation is that we typically have nonlinear systems when we talk about cold atoms, which means that we describe our systems using the Gross-Pittievsky equation, where this A sub s is our interaction strength. And so what we would typically expect is that if we take a slice of cold atoms, so a two-dimensional slice of cold atoms, and we move it through a potential in the z direction, so we're going to move our cold atoms down, that we would expect to see features that develop into dispersive shock waves. Okay? But like I said, we want to know what happens when we no longer have interactions, but we still have dispersion, because we still have free particles. Okay, so we still have a free particle dispersion. All right, so don't worry, all of those guys are going to be zoomed in here. So the first thing we want to do is we want to just start with a very simple model. Okay, so what we're going to do is we're going to apply an absolute value potential to the atoms. Okay, so this is the reason that this is the simplest model is because then we have atoms that are being pushed to the left, atoms that are being pushed to the right, and they're going to interfere. Okay, so if we let this evolve, we can imagine that we're starting with our atoms. Let me make sure I don't press next. We're starting with our atoms up here, and they're being the absolute value potential is being applied, and we can imagine this z, which is where the atoms are being dragged. Okay, we can also imagine that as being kind of a time axis. Okay, so we can see this beautiful, nice dispersive shock wave that forms, and just ignore these rarefaction waves that happen at the edges because that's just from boundary conditions. All right, so now if we don't have interactions, we expect something that looks more like this, where instead of having an expanding dispersive shock wave, we get, and again, ignore everything happening on the edges. I tried to cut the video down. But we have more of a dispersive wave that's a very high frequency, and it doesn't expand like you would expect to see in a dispersive shock wave. Okay, but this is an absolute value potential. It's not really physical in our system. And so what we want to do is we want to look at a Gaussian potential instead. Okay, oh, this is the combination, sorry. This is the combination of all three. So we can, see right here, is the healing length, and as we increase the healing length, that means that our interactions are becoming weaker and weaker. So we can imagine this being going from interactions to no-ish interactions. Okay, so very, very weak. Okay, so now if we have an attractive Gaussian potential, which means that we have a well that we drag our atoms through, so we can imagine this little cartoon here, this circle represents my little Gaussian potential. And so I'm going to imagine that my trajectories of my atoms are going to cross somewhere in the middle, okay? And so when we do this, we expect that we're going to see this beautiful dispersive shock wave that's created. Okay, again, edges, boundary conditions. I didn't make these simulations. They were kind of given to me, and I am running with it, okay? So we've seen this before. This is a very standard type of thing that we would see in a BEC system if we take an elongated BEC and we apply a pulse in the center, because as we're dragging our atoms through this potential, this is equivalent to pulsing on and turning off. Okay, so we've seen this before. Okay, so this is what's kind of expected. But now let's turn off the interactions. Okay, so again, this is where the healing length has been made very, very large. And what we see is we again see these high frequency dispersive waves going out to the side. And then, fun enough, we have a constant 1 background. And then we have this thing that looks kind of like an airy wave. The envelope looks like an airy wave, and you get these oscillating solutions in the middle. Okay? And so this is what we're going to be looking for. So again, here's the with interactions to no interactions, and you can see how these three systems compare to one another. Okay, so now, we also have a repulsive Gaussian potential. Because we're experimentalists, we like to poke our atoms with different things. That's just what we like to do. And so we can imagine that, again, here's my little cartoon with my repulsive Gaussian potential, so it acts like a hill that the atoms have to move past. Okay? And so what we would expect to see is we have these high intensity, essentially paths that the atoms are taking, and because there's a uniform background, we're going to get dispersive shock waves as we steepen, and then in the center, we're going to get a collision of two dispersive shock waves. And again, high frequency noise, that's just edge effects. Okay, that's just because I didn't cut down the video. Okay, and again, this has been studied, this has been shown. So if we take an elongated BEC and we apply a pulse that's repulsive in the center, this is what we would expect to see, and this has been shown in experiments. Okay, but without interactions, things are slightly different. We again get those dispersive high frequency waves. We again get those kind of airy type solutions in the envelopes. And then we don't have anything in the center because there's no more mean field pushing the atoms back into where the void was. Okay, so we no longer have our mean field interactions. So again, comparison from, and yeah, the noise, yeah, okay. Okay, so what we see when we have zero interactions is we see the emergence of what we know as caustics, okay? And so today I'm going to be showing you some beautiful pictures of actual experiments, okay? So as you probably know, so Michael Berry kind of introduced my talk on Monday, which was great because he started talking about caustics, and his work, much of his work was on caustics, and a lot of what we know about caustics is actually from his theories. So we have envelopes of light rays that form when light's reflected or refracted from a surface. Here are just a couple examples. Gravitational lensing is an example of a caustic as well as a rainbow. And then these are a couple pictures that I took because once we started studying caustics, I started seeing them everywhere. Okay, so if you have two rays that come together, you get a fold. Okay, these are just the types of caustics I'm going to be talking about. And if you have three rays coming together, so if you have one ray coming right here, one ray coming from right here, and one ray going down the middle, you get a cusp, okay? And so we're going to be talking about these, and these ideas about caustics are well described by catastrophe theory. So this is our road to catastrophe, if you will. All right, so it's not totally unheard of for people in cold atoms to be wanting to look at caustics. It has been done by some other people. So this is being released from a magneto-optical trap. So that was this work right here in 2014. Here's an example of that experiment. Of course, these are individual time slices that were put together. Okay? Here is some work done in 2009 from diffracting from a 1D lattice. Okay? Again, these are individual time slices. They aren't one full picture. It's all put together. This is some theory work that was done in 2009 in response to a 2008 experiment by the Hewlett group on expanding BECs when you vary their initial phase. Again, time slices. Okay? And then we have our work right here, where this is a single image that we've taken. Okay, so this is one image taken over all of the atomic trajectories. Okay, so a different type of platform to look at this work. And so how we start is we start with our Bose-Einstein condensate, which is a coherent matter wave. Okay? We have confinement with an optical trap, and then we provide an additional kind of help with the trap with a magnetic gradient. Okay? And so if we have our atoms in a specific state, they will be trapped. But then if we put them in a state that doesn't really like to be magnetically trapped, they fall out. Okay? So we start with our atoms, which are rubidium-87 atoms, and the 1-1 trap, which is magnetically trappable. And we have our interaction strength at this point. Okay? But then what we want to do is we want to take a slice out of our BEC and flip it to a different state. And so what we do is we apply an RF or a microwave tone, which then outcouples atoms into one of these 4 states. So these 4 states do not like to be magnetically trapped, and so they will fall out of the BEC, out of the trap. Okay, so this is because that magnetic confinement isn't really helping it anymore. They're just kind of falling. So this is a single image of what our atom lasers look like. This was taken in 2021, and this is being transferred to the 2-2 state, which means that we have an acceleration of the atoms that's about 3 times gravity. But if we go to different states, we can change that. So if we go to the 2-1 state, well, then we're only at about 2 times gravity, versus if we go to the 2-0 state or the 1-0 state, we're approximately at gravity. So we can change how fast our atoms are being accelerated in the system. Okay? And this also creates this large area field that we can probe. We can just poke it with things and see what happens, and it's super fun. Okay? So we have about 240 microns in this direction, about 600 microns in this direction. So this is a very large area that we can start to probe different types of fields in our systems. And again, these are no interactions. Yeah?
Is this a steady configuration?
Eventually, we will run out of atoms. But the main limitation we have is just how much imaging space we have. So our atom laser is pretty close to the top of our imaging, like of where our camera can image. And we can go about 10 microseconds or 10 milliseconds of outcoupling, and then our atoms are at the bottom of our camera. And so we're mainly limited by that. But again, we can slow down how fast the atoms are going and be able to do this for longer and longer times. Okay, so now I told you I was going to poke it. I'm going to poke it. So we have 2 different potentials that we're using in this case that are far detuned. Okay, so that means that that any spin state we're in, they don't like these potentials. Okay, so I'm going to define some terms that I'm going to be using. So there's an injection point. That's where our BEC initially is. Okay, and then there's this H term, which is the distance below the initial BEC where our potential lies. Okay, so if we take the height of the potential and we calculate what the kinetic energy is based on the acceleration and the distance that the atoms fall, if we take the ratio of that, we have an epsilon term. Okay, so that's where that epsilon term, which you're going to see, is coming from. Okay, and just to point out, these types of systems are highly tunable, which is one of the reasons why we really like them, because we can tune lots of different parameters. Okay, this is our setup. We have our camera, which is going to take the picture. Here is our trap, and we're going to outcouple atoms in this direction, and we're going to poke the atom laser, and we're going to be able to image along this axis. So we're taking the picture from the front of the atom laser. We're going to start in our F equals -1 state, and we're going to apply a single microwave tone to be able to go into this F equals 2 - 2 state. again, this is like as much math as I'm going to show in this talk. This is mainly about pretty pictures. I just want to wow you with these. Okay, so these are images from our experiment. Okay, again, each one of these images is well, technically these are 6 images for each one of these panels averaged together. So this is extremely reproducible. And so each one of these, so this is for the repulsive case on top, is for a different potential height. Okay? So we can see that as we increase the potential height, and I don't know why my equal sign looks like a minus, those are epsilon equals different things, okay? As we increase the potential height, we see that we have these attached fans that we can measure the angle of. And then at about epsilon equals 1, which again is when the potential height is approximately equal to the kinetic energy of the atoms, we get this kind of fuzzy region where we have a little bit right here, and then there's a very faint detached shock up here. And then when we go above 1, we can see this very clear detached shock. Okay, I call it a detached shock. It's not really a shock. There are no interactions. But it looks kind of like one of a detached Bose shock. Okay, down on the bottom we have our attractive potential, which is why all of these epsilons are just negative. And apparently you can see equal signs on the bottom. I don't know why. And we can see that we go from having something that looks very collimated to, again, having these fans. And just as a reminder, our atoms are going through the potential. So atoms from over here are going through the potential this way, and atoms from over here are going through the potential this way. And as a Gaussian, you can imagine that you have a much flatter top than something like an absolute value potential. So you're going to have more atoms that just flow through the center. Okay, so if we compare these types of things to things that we recognize, our attractive potentials can be kind of thought of as a detunable lens, which is fairly popular these days. And then we also have things that appear to be very similar to things like oblique shocks and detached Bose shocks, like I mentioned. Again, we don't have interactions. These aren't actually what they are, but they sure look like it. And in quantum, in cold atoms, we really like to talk about simulators. Okay. All right. So then if we think about caustics, we think about folds and cusps. And so if we look at our repulsive case, what we actually have, if we put this in as a sheet that's folding over itself, okay? So we have 1 fold, 2 folds, it goes through 0, 3 folds, 4 folds. And this comes from one cusp caustic, the cusp caustic happening right here, which is where you have a singularity that goes into many folds, okay? In the case of the detached like Bose shock, we actually have an infinite number of folds because the atoms right here constantly bounce back and forth. Okay. In terms of the attractive potentials, we have 2-fold caustics, so 1, 2, okay, coming from one cusp caustic, which is very clear right here. Okay, so you may have been looking at some of these pictures earlier and been like, those may look like Pearce integral solutions. Well, they sure do look like it, and if we zoom in a little bit to one of our old images, it looks like that's exactly what we're seeing. However, when we changed our imaging optics, we found that a lot of those features went away. And so we think that what's actually going on here is that these sharp caustic features are extremely sharp. They're almost like knife edges. We are limited in our imaging by our optical resolution of about 3 microns. We expect that these caustic features are actually sharper than that. But because we have light going through them, we see diffractive effects. Okay, so this is still something that we're thinking about, but just wanted to point out those commonalities you may have been thinking of. Since yeah. Mm-hmm. Yeah, so what we would expect to see, though, if we were able to resolve these types of features, is it would be like 2 airy waves interfering with one another, those types of things. So we see like diamond shapes in here, but our resolution isn't good enough to be able to actually see those features. But we're looking into ways to be able to do that, because that'd be really cool. Okay, so we can do more. We can actually start tracing the flow of where atoms are. So if we take our single microwave pulse and then we start pulsing atoms back into the other state. We're imaging on the 2 state, which means that we can't see atoms in the 1 state. Okay? So those appear as dark notches in our image. Okay? And so if we take one of these notches, that's at a fixed time. So those are all atoms that have been emitted at the same time. Okay? So if we follow some of these, let's see if it works. Yeah. Okay? So there's the notch from atoms that haven't been affected by the Gaussian potential, and then they bounce up. Okay? Over here, we have a kind of bow tie thing that happens where atoms are pulled around. Okay, so in this way, we can directly see how the different atom flow is occurring around these caustics. And as a fun connection, Einstein rings have a very similar type of visualization. Of course, these are plane fronts, and what we're looking at are constant times. And so that's the only reason that these two things look different. We can also just outcouple just a single slice of atoms, and we can watch as this evolves. Okay, again, each one of these is a different experiment because every time we take a picture, we destroy it. Okay, but this is extremely reproducible, which is one of the reasons why we love it. Okay. And as a fun aside, I already made the connection to Einstein rings. Well, if you have multiple potentials, so let me back that up. If you have a left well, so a left attractive potential and a right well, and you turn them on, they look pretty normal. If you turn on both of them, you see something that can look like a collimated kind of column, which is where you have your trajectories are actually going around in here and then coming out, very similar to a double Einstein ring that you can kind of imagine here. So that's just fun simulations. We're still looking into connections. Okay, so I have very little time left, but I really want to show you these pictures because they're my favorite pictures of all time. Okay, so instead of having repulsive for all of the states of rubidium or attractive for all of the states, we can actually look at a different type of potential, which is the potential that exists between the F=1 and the F=2 states. So somewhere right here. Okay, we can do this by locking onto a rubidium 85 line, which lives right there. It's very convenient. And what that turns out to be is that for the 2-0 state, we have a repulsive potential, and for the 1-0 state, we have an attractive potential. And so this differential potential is something that we're going to use. Of course, because it's really near resonance, we can't actually have very high powers. But one of the things that we learned from our caustics work is that you can re-engineer your optical potential by looking at what the caustics look like. So this is kind of the real inverse scattering problem, if you will. Okay? And so if we have really weak potentials, we still want to be able to do this. And so that's what we're going to do. But if we do that, this is what we see. Okay? There's not really much caustics going on. And so, we want to be able to actually image what the potential looks like. And so what we do is we use atom interferometry. Okay? And so after we create our atom laser in the 2-0 state now, so we're in a different state. This is the magnetically non-susceptible state. We're going to create a superposition. So we're going to apply a pi/2 pulse, take our atoms from here, move them here. Okay? We're going to let it evolve for some amount of time in the order of like 100 microseconds. And then we're going to close our interferometer by applying another pi/2 pulse. Okay? This is a Ramsey pulse sequence. It's fairly standard in atom interferometry. And so what's going to happen when I do that? Out pops my potential. Okay? So going from here to here. And so these are complementary states of each other. If you put these two images on top of each other, you get nothing. Okay? So this is pretty cool. And it turns out that, so this only requires phase imprinting. There's no actual counterflow. It's too small of a time for counterflow to happen. Okay? They're evolving at different phases because they're affected by the magnetic field slightly differently. Okay, so on the right of each of these panels is our experimental data. These have been averaged over 30 images. Okay, so you see that the reproducibility of these rings is pretty good. On the left is our theory. Okay, so this is another way that we're able to kind of fit or re-engineer our optical potential by using these types of atom laser experiments. Okay? But, you know, it might be that you want to know your potential a little bit better. And so one thing you can do is you can use phase shifting interferometry to do this. So essentially you're doing the exact same thing that we were just doing, except for now I'm shifting the phase of my generator by some delta phi. And that delta phi is indicated down here. Okay? And so what I can do is I can do a 10-step algorithm, which the 10-step just happens to be because I took 2 pi and divided it by 10. Okay? I take this 10-step algorithm, and then I unwind it. Okay? And there are different algorithms that you can use for this. We used a couple algorithms that are cited here. And so I can recreate my optical potential. So I can recreate a surface of this. So this downwards tilt is my magnetic gradient, and this hole right here is my potential. So that's kind of cool. We can recreate potentials that are extremely weak. Okay? But then what if I want to just pulse on something? Everything up to this point has just been just leaving on a potential and letting the atoms fall through it. But what if I create my atom laser and then I pulse on a potential for a microsecond? Well, if I just do regular absorption imaging, which is how we typically do imaging, this is what I see. It looks like an atom laser. It doesn't look like much. Okay? But now I change my procedures so that I do this atom interferometric imaging, and this is what I get. Okay, so now we can see exactly where the potential is. And so you can imagine that if you have an atom laser next to a system that has strong magnetic fields, you can actually image those fields pretty well. Okay, so we're looking into applications for using these types of atom lasers in these types of systems for looking at stray magnetic fields and being able to characterize magnetic fields in a system. And again, only phase imprinting. Okay, so here's a summary. We've generated clear caustic features in a very reproducible system, and we have imaging resolution limits, and we really want to see our airy waves. We really want to do that, and so we're looking into ways that we can do that. And this new atom interferometric imaging technique is really promising, and we're looking forward to pursuing that a little bit further. So just as a aside, all of this research was completed at Washington State University. Of course, right now, it looks more like this. It's a little bit snowy. University of San Diego always looks like this. It's beautiful. If you're ever in the San Diego area, please let me know. We're at the top of the hill. You can see the ocean and sea world from campus. And I'm the only quantum person there. Okay, so I don't have theory support at my university, but we do have a lot of great theory at University of California, San Diego, as well as SDSU, San Diego State University. But I am looking for theory collaborators. I'm currently building a new lab that's going to do two-dimensional, two-component mixture BECs across the miscible to immiscible regime, and I'm looking at interface dynamics. Okay, so if you are very excited about that kind of stuff and you're patient to let me finish building my machine, then I'd love to chat with you. But I do only work with undergraduate researchers because I am at a primarily undergraduate institution. And so right now we're building up this lab just with undergraduates, which I'm sure you all know can be interesting. They aren't around for very long, that's for sure. Okay? And so here are some potential directions. I'll leave you with this. We're looking essentially at moving towards introducing interactions within our system and seeing what kind of dynamics we can see there. So, thank you.
Thank you. Is there any question in the audience?
Everyone's excited for lunch.
Thank you. I really enjoyed your talk.
Thank you.
I understand that the wavelengths of your wave is kind of small compared to the size of the potential. But could you increase that? So, for instance, maybe you would then be able to see nucleation of linear vortices?
I don't know if we'd be able to see that in an atom laser setting, because even though we are still coherent, we our density is extremely low. And again, we don't have interactions, I think, to support those types of features.
You don't need interaction for having vortices. I mean, you need a zero of the wave function.
Yeah, that's true. I mean, there are things that we're looking into in terms of generating dynamics within a BEC and then outcoupling to see if we can actually do a time kind of sequence, because what's really cool about the atom laser is that you get a single image for a 7 millisecond or 10 millisecond time scale. And so if you outcouple things that have dynamics, you can trace those types of things back in time, which is really cool.
Okay.
Yeah.
And then we can talk Shimshon Barat at
Absolutely.
Tel Aviv. I've done an experiment that reminds me of yours.
Yeah, yeah. I hope you enjoyed all the pretty pictures. Now you can have a nice snack before lunch, that type of thing.
Is there a question? At some point, you showed a very nice airy diffraction pattern without interaction.
Mm-hmm.
So this, I understand, is a large-scale structure, but I missed why there is a fast oscillatory structure inside this.
Well, I think that still comes from the fact that there's dispersion in the system. So there's still dispersion, there's just no interactions. And so instead of having a dispersive shock wave, if you will, that expands, you still get this kind of envelope on the inside with those high frequencies. And I believe that those are from the dispersion, the fact that we still do have such dispersion.
Okay.
Yeah.
Thank you. So let's thank our speaker again. And before you go for lunch, I think that Mark has an announcement to go.
So we were informed by I&I staff that the Churchill College is going to be very crowded today. They can't accommodate everyone who has a ticket, but those who are going to drop in, you go at your own risk. They may turn you away, or they've advocated that those who do not have a ticket for lunch not go to Churchill. The alternative is just here. The building here is a canteen. There's food options there. And I will remind you that we still have 3 more talks this afternoon. Those of you thinking about escaping after lunch, we hope you come back, and let's round out this great workshop. Enjoy lunch.